Hi, folks. I hope you had a great long weekend, enjoyed your Thanksgiving. Today, your job is to figure out how to factor a sum or a difference of cubes. The formulas for this will always be posted, and you'll always be able to follow the pattern. So the mission right now is to sort of discover that the pattern that applies, and then also understand why some of the components of it are true all of the time. Okay. So my advice would be pause this, go do the getting started activity using the factor theorem, come on back, and I will have filled in probably one of each example because they're going to be the same. Okay. So you go do you and then come on back. Okay. So remember factor theorem, you're going to pick a number and you want it to be equal to 0, right? So here, if I'm looking at this, I'm like, what cubed is going to be the opposite of -8? So I want 8. So I'm thinking 2 should work, right? So this would be like f at 2 equals 0. I guess I'm going to write an orange pen because that's where we started. I'll fix it on the next slide. So again, you can use synthetic division or whatever you need to use to find your roots. So we're going to put in a 2 and then 1, 0, 0, and -8 because we have no x squared term and no x term. So this is called a difference of cubes because it's a perfect cube, subtract a perfect cube. So same idea as a difference of squares. And then 2 times 1 is 2, 0 plus 2 is 2, 2 times 2 is 4, 0 plus 4 is 4, and 2 times 4 is 8, which gives me no remainder. So my factored form of this, so x cubed minus 8, would be the same as x minus 2, and then x squared plus 2x plus 4, because we want to reduce by 1 degree. I'll just do both for the heck of it. This one would be like f at 3 equals 0. So same thing. 1, 0, 0, -27, 1, 3, 9, 27, and 0. So in its factored form, this guy looks like that. Okay. So if you did spot a pattern there, what you should see is that your binomial factor has subtraction in it, and then your quotient or your trinomial factor has all positive signs in it. The numbers have some relation too, right? Like 2 is the cubed root of 8, 4 is the cubed root of 8 squared, the middle term is still the cubed root of 8. So there's some stuff going on there where both of these look pretty similar. Like the 2 and the 4 seem to fit with the 3 and the 9, etc. We'll talk more about what's happening and why it's happening. What I do want you to look at, though, is this part here will never be factorable. Okay, so no matter what you're dealing with, you cannot factor that trinomial. Okay, and most people will try to prove me wrong. You'll try it a few times. Sometimes you even make it factor somehow, but it isn't, okay, ever, because think about what you're drawing. Okay, so here we are talking about this graph, right? So that's y equals x cubed, shifted down 8 units, right? So if I went down 8, it still looks the same. So down 8 units. It's only going to have one x-intercept. And no matter what, the graph's just going to have one x-intercept. Okay, so only one of these is a real root. So the 3 and the 2 that you found are the only answers. You can't factor, you can't quadratic formula, you can't do anything with that remaining trinomial. Okay? And then again, you can fill in that you see a pattern in the terms with whatever you want. But there is a pattern there, right? At least if you can keep track of what signs go where. And then when we get into it further, you'll see what the pattern is. I also gave you sums of cubes. So in last year and, well, grade 10 and grade 11 and this year, we talked about differences of squares, and we've been like, there's no such thing as a sum of squares because there was no value that would make it equal 0. You can't square a number and then add to it and get nothing. However, with cubes you can. So the second set of examples, the only difference is that you would have to put in -2 to get that 0. Okay, so we're just going to have some signs change on us here. Oh, that's what I did. I'm like, what the heck did I do? That needs to be a -8, but that needs to be a +4. Okay, that's what you get for working quickly. So this guy would factor to be x plus 2 and then x squared minus 2x plus 4. Okay, so again, it's easier to look kind of sum versus difference and see like that the signs switch, right? So the binomial factor has addition in the sum of cubes, but then in the middle of your trinomial, you're going to have subtraction. This is the exact same graph, it just shifted up 8, so it still only has one x-intercept. So you're not going to be able to factor that trinomial. Okay, and the sum of cubes with the 27 does the same thing. So by prediction, I would say that that factor should have been when you finished x plus 3 and then x squared minus 3x plus 9. It's just a little sign swap in there. Again, summarize your patterns as you wish. But the mission for today is to talk about how we go about factoring sums and differences of cubes to save you some time. So as you just saw, like the factor theorem works. So you can find that value that makes it 0 and run through synthetic division and do all that. That's fine. But you'll start to see some nasty ones as we go through these examples. And when you run into those, you want to be able to recognize a sum or a difference of cubes, similar to how you wanted to be able to factor a difference of squares efficiently. Okay. Today is October. I'm struggling with this pad today. There we go. So you're watching this on the 10th. Voila. So a sum of cubes by definition is an expression that contains two perfect cubes that are being added together. Okay, so a cubed plus b cubed, and those are big capital letters to help us with the pattern. And then I've given you an example where a is not 1, like the coefficient of x cubed is something other than 1 underneath, so 27x cubed plus 8, because both of those have a cubed root, right? So it'd be 3 and 2, or 3x and 2. Every time you guys factor a sum of cubes, you end up with the cubed root of a plus the cubed root of b in your first bracket, and then your second bracket is like that cubed root of a squared and the cubed root of b squared on the ends, and in the middle is the product of the two cubed roots. Okay, so to factor that 27x cubed plus 8, the cubed root of 27x cubed is 3x, the cubed root of 8 is 2. So I know my first bracket has to be a plus b, so it's 3x plus 2. And then I know that my second bracket has to be a squared, so it's 9x squared, right? 3x times 3x. The middle term is negative, the product of, so 3x times 2 is 6x, so I'm going to subtract 6x, and then 2 squared is 4. Okay, and that's how it sets up every time. So if you can identify that big A and big B, then it's easier to fill in the brackets. Okay, differences of cubes, same thing, perfect cubes, but one is being subtracted from the other. And your pattern is just a little different. So the binomial is a minus b, and then you have all positives in your second bracket. But the pattern of terms is the same, so a squared, ab, and then b squared. Okay, so the difference underneath, again, factors to look very similar, just the two signs flip. So the easiest way to see this is to do it. So we'll start with one that is pretty straightforward, and then they get worse as we go. So number 1, the cube root of 64x cubed is just 4x. Okay, so a would be 4x, and b, the cubed root of 125, is just 5. Okay, and it's a sum, so pay attention to that sign. And then when you go to factor it, you want 4x plus 5, and then you'd have 16x squared minus 20x plus 25. Okay, and that's just following the pattern from the previous page. Okay, so a plus b, a squared minus ab plus b squared. Okay, number 2, you guys are going to look at and go, Miss, those aren't those aren't perfect cubes. Please don't take the cubed root of 16 and give me some nasty looking decimal or some sort of exponential expression. Common factor. So I see two even numbers. I feel pretty confident I can take a 2 out of there. And then I have exactly what we've already kind of seen numbers wise. So now I'm going to look in here and identify A as 2x and B as 3. So I would still have that 2 out in front, and then 2x minus 3, 4x squared plus 6x plus 9. Okay, no matter how hard you try, you can't factor that trinomial, so don't try, right? You're dealing with a regular cubic function that's being shifted up and down. It has one x-intercept, that's it. So these are imaginary roots over here anyway. Now, that was kind of a twist, but hopefully you guys would think to common factor by now, because that's usually the best way to solve a problem when you look at a factoring question and think it's impossible. Hopefully, if you take a look at number 3, you will see why you don't want to use the factor theorem here. Okay, so we want to actually take the time to learn the pattern or see the pattern or recognize that it's a sum of cubes, because I don't want to expand those out. I don't want to expand and simplify and get this thing into a standard form and then use the factor theorem to factor it. Okay, I could, but I don't want to. So what you want to do here instead is go, okay, that's a sum of cubes. So I'm going to take that and this and let those be A and B. Okay, so A equals x plus 4 and B equals 2x minus 1. And I'm going to remember that my pattern is A plus B, A squared minus 2A, nope, minus AB. Let's just try that all over again, plus B squared. Okay, so now I'm going to work, I would rather square a binomial than cube it. Okay, but you have to also like do good algebra while you do this. So A plus B is going to be x plus 4 plus 2x minus 1. Okay, now A squared, remember it's not x squared plus 16. It's going to be x squared plus 8x plus 16. Okay, so I'm going to do a bunch of these kind of off to the side just to reduce the amount of clutter on the left. A times B is going to be 2x squared, and then I would have plus 7x and minus 4. Okay, so I got like a negative x there and a positive 8x. So that's where that 7 came from. 4 times negative 1 is negative 4. And then b squared, again, is going to be 4x squared minus 4x plus 1. Okay, so don't lose your middle term. So now all of those are going to go in here. Okay, so x squared plus 8x plus 16 plus 2x squared plus 7x minus 4 plus 4x squared minus 4x plus 1. Now you just want to tidy up in your brackets and you're good. Okay, you factored. So I'm going to have 3x plus 3, and then we can common factor a little after as well. Then I have 3x squareds and 4x squared, so 7x squareds, I think. And 8x and 7x is 15x, minus 4 is 11x. And then I have a 16, 12, 12 plus 1 is 13. Okay, and then I have a 3x plus 3 there, so let's take a 3 out. So 3x plus 1, 7x squared plus 11x plus 13. Okay, if you don't recognize it as, oh no, there's a sign error, guys. This is why I need to be in class with you. I have to subtract in the middle there. The first term's right. The second half is wrong because I plugged it in incorrectly into the formula. I need to subtract 2x squared and subtract 7x and add 4, and then I can put 4x squared minus 4x plus 1 back in there. I'm so sorry. So negative x squared plus 4x squared is 3x squared. 8x minus 7 is 1. Minus 4 is negative 3x. That makes more sense. I thought more stuff canceled. And then that's a 16. Plus 4 is 20. Plus 1 is 21. There we go. Okay. And now this also has a common factor of 3. So a 3 can come out and get multiplied with the 3 that's there. So 9 times x plus 1 times x squared minus x plus 7. Okay, so problem solved. Sorry about that. Make sure you use the subtraction and make sure you distribute your subtraction sign through all of AB. Okay, so it's not just in front of the x squared, it's through the entire thing. But hopefully you can see where using a pattern makes that more efficient than expanding and simplifying, collecting your like terms using the factor theorem. And then it's kind of like a needle in a haystack. Like in this case, your factor theorem would have been -1, so that's okay. But again, you're only going to have one answer, so most of the time. So be careful about expanding. You should be able to factor from the form it's in. Okay, and then number 4, remember that a cubed root is the same as the exponent of 1/3. Okay, so the cubed root of something like x to the 9 could also be written as x to the power of 9 to the 1/3. And then if you multiply your exponents, you get x cubed. Okay, so a equals x cubed and b would equal y cubed. We're dealing with a difference this time. Okay, so when you go to factor, you'd have x cubed minus y cubed. And then remember, if you divided, so you subtract your exponents, so your x to the 6 is going to be what you end up with here. Okay, so again, it's this squared, but just to remind you, that's what's happening, so that when we expand, we actually get our answer back. So x cubed squared is x to the power of 6. This time I add the product of them, x cubed, y cubed, and then I'm going to add y to the 6. Okay, so that's great. That's all fine and wonderful. But this is another difference of cubes. Okay, so again, you just have to apply that whole process a second time. So the cubed root of x cubed is x, and the cubed root of y cubed is y. And then I would have x squared plus xy plus y squared times x to the 6, x cubed, y to the 6. Okay, so the homework today is basically just applying the pattern to some funny looking questions and to some basic ones. So try that, do that. It's a more formulaic way to factor than taking the factor theorem and taking guesses. So hopefully you enjoy that a little more. But good luck, have fun. And then tomorrow we'll talk how to solve polynomial equations.